So the question is, why are we studying Tetris? From a professor point of view.
Hi, my name is Shimon Shoken, and in the next 10 minutes I'm going to tell you about a new approach for teaching applied computer science, an approach that I developed together with my colleague Noam Nissan from the Hebrew University and from Google Research.
So the next question might be, why are we using electronics? Why can't we be focusing on some other topic in engineering? Well, this isn't electronics. This is much more fundamental than electronics. For example, we could teach this with Minecraft.
Hello there everybody, it's 101 here, and this is my almost completed CPU. Here is an XOR gate. It's very compact, and the usual problem with XOR gates in Minecraft is they take 2 or 3, maybe 4 ticks to run. Now this one performs its operation in 2 ticks, very nice and fast.
So you can see that you can build an entire computer with blocks inside of Minecraft. And we can do this with Legos. So here you see one Lego NAND gate, and there's many ways to build these NAND gates inside of Legos. But we can also do this with inside industrial automation. And so its symbol is right here. And these devices right here they could be a valve, they could be a device that's on or off, like a motor. They could be a package that's present on a conveyor belt or not present on a conveyor belt. That's what these two symbols represent. So this would be a conveyor belt, this would be a conveyor belt. This would be a valve, this would be a valve. This would be an on-off device, this would be an on-off device. So when you study industrial automation, you're studying the exact same thing. So there's not much difference between Minecraft and
staggering 15,000 parcels per hour on a total of 20 available in-feed lanes. Each parcel is scanned, weighed, photographed, and sorted.
So the big question then is, why specifically Tetris? Why use electronics as an introduction to this whole world? Well, the first reason is that Tetris is using the standard symbols. This is a part of the textbook that's online, that's at Tetris's website, and you can see here they're using the standard symbols of Claude Shannon. Claude Shannon is the MIT professor that created this. He died in 2001. He's a professor at MIT. He's basically caused the revolution in electronics that's moved us out of the 1880s Maxwell's equations world of capacitors, inductors, and resistors and into the digital age that we're part of right now. So I'd like to start this introduction to Tetris with their official introduction that's at a MOOC site, Coursera.
Anyone can take this course, including people who have no background in computer science or engineering. The course consists of 6 weekly projects, each focusing on building a different module of the computer's hardware. In each project, you have to build a set of chips. And for each such chip, we provide a complete chip specification, and you then have to figure out how to build this functionality using chips that you've built before. But don't worry. You will have to do no soldering whatsoever. Instead, you will build all the chips using a hardware simulator, just like hardware engineers actually do in practice. In the first three projects of the course, we start with the most elementary logic gate called NAND. Using detailed project materials, we will guide you through the process of building a chipset, a central processing unit, and a memory unit. In the next two projects, you will integrate all the chips that you've built before into a complete general-purpose computer named Hack. We will then connect the computer to a keyboard and a screen, and poof, the computer will snap into action. In the last project in the course, we develop an assembler which enables writing programs using symbolic commands rather than binary code. This will allow us to use the Hack platform to run all sorts of cool programs like Tetris and practically any other program that comes to your mind. And that's it!